Hey, this is Greg from CacheQ, and we often get asked what is the difference between our compiler and OpenMP, and I thought I'd do a quick video and basically run you through some of the major differences between these two technologies. First and foremost, our compiler extracts parallelism for shared memory, multi-core processors, and heterogeneous compute platforms. And before I get too far into this video, I would like to contrast that with and show you a quick video clip of one of the founders of OpenMP, a guy by the name of Tim Matson. He works at Intel, and he's a principal research engineer. He's one of the people that developed OpenMP. And here's what he has to say about whether or not what we do is possible.
After 2 or 3 decades of research, automatic parallelism has utterly failed time and time again. So I'm sorry, we are not going to be able to create a magical compiler that takes your serial code and creates parallel code for you. Ain't going to happen. Don't waste your time. You're going to have to roll up your sleeves and you're going to have to parallelize it yourself.
Okay, wow. So those are some pretty strong words from Dr. Matson. And in his defense, he did say that well over 8 years ago or so, when they were first recording all of these tutorials on OpenMP for YouTube. So I haven't talked to him. I don't know whether he still feels this is possible or not, but just to reiterate, he doesn't think that this is possible. He thinks that that all these attempts have utterly failed and ain't gonna happen. Don't waste your time. Well, I'm here to say, maybe that was true for OpenMP. Intel spent 20 or 30 years looking at this and they have failed. But we have succeeded, and I'm going to demonstrate that for you. So here's the magical compiler that you have been waiting for. Let me just start by running through some of the benefits for OpenMP. First, it's free, which is pretty big, but sometimes you do get what you pay for. It is technology that was developed in the 90s, and I'm going to make the argument, of course, that we have evolved and there's some additional value there that is worth engaging with a company like CacheQ. It's available everywhere. It's pretty much integrated into all modern compilers today, including the new compiler collection, ICC from Intel. Pretty much every compiler kind of has it. It's just enabled with a switch. It's taught everywhere. Most universities include courses where they talk about OpenMP. When you begin to talk about parallelism in software, it's pretty much what you use to understand. And it works pretty well with some caveats. First of all, you got to know what you're doing, which means you need to spend that time learning about parallelism, about what it means. And you also must know some things about the hardware on which you are running, particular things like cache line sizes, and that stuff is not trivial. And then even once you do learn that stuff, you're going to be experimenting quite a lot, writing and rewriting code, measuring performance in order to gain that parallelism. So, hopefully you don't have a pointy-haired boss standing over you suggesting that you use OpenMP and dismissing how easy it is, because it's really not easy to learn. What does OpenMP look like? Here's some code that has a screen capture of the training videos on OpenMP. It's really not easy to learn or use. You're going to spend probably many days, if not many weeks, learning this for the first time. And even once you know it, you're going to be experimenting quite a lot to extract parallelism out of your serial code. So, first thing you notice is you're actually modifying your code. You're including header files. You're manually controlling the number of threads. You're explicitly telling the compiler what to parallelize. It doesn't just go and do it. You have to tell it what can be parallelized. Not only that, you have to get into understanding of private versus shared variables between multiple threads. and you're going to be writing code that is specific to the number of threads that you're on. And then pretty quickly you're going to realize, wow, I got it to run, but it's not very fast. So what's going on? And then you're going to learn about this thing called fault sharing, which is when you're accessing the piece of data that's in the same line of cache across multiple threads. They invalidate each other, and therefore it's not going to perform as fast. You're going to rewrite your code and fix that, and then you're going to realize, oh wait, now I'm getting the wrong number. I'm getting the actual wrong results. What in the world is this? And then you're going to realize, oh, there's race conditions. Some threads are finishing before the others, and you have no control over them. You have to explicitly put in synchronization, and you're going to be iterating and iterating, iterating. And, you know, I really can't believe that Tim and Intel and the people involved in OpenMP haven't figured out a better way to do this. Well, actually I can, because it's actually very, very hard. And this is what we do at CacheQ, and that's the major benefit of QCC. So I'm here to tell you that automatic parallelism is possible. So you can believe it. It doesn't require pragmas or rewriting of code, refactoring your code in order to make it run in parallel. Furthermore, we guarantee that our results always match the single thread GCC. And the reason we do this is because we build a data flow graph, which is a custom virtual engine implementation using our own instruction sets that runs on top of either the instruction set architecture of the device or will run in hardware. And I'll talk about that in just a second. But inside this data flow graph, we understand the dependencies, and therefore we ensure that things operate first in parallel in a pipeline, and then in the correct order. Not only that, we provide a bunch of analysis tools to help you understand threading and parallelism inside your code, which you don't get at all with OpenMP. We have visualization tools that help you understand what we're building, and we have reporting tools that tell you if something isn't threadable, why not, and what lines of code you're in. And that virtual engine that I mentioned, it's already inherently pipeline, which means it'll run in parallel. The compilers are typically limited to the superscalar pipelines built into the actual CPU architecture. We build pipelines on top of that for implementation in things like heterogeneous accelerators. And because of that, we can also thread certain types of loops that OpenMP simply cannot, so we get better QOR. And then the final result is there is a path to targeting heterogeneous accelerators in FPGAs, and we're also working on GPUs. We have accelerators today. So not only do you not have to refactor your C code, you also don't have to find a hardware design team to go and rewrite this in hardware description languages to make use of hardware accelerators such as FPGA cards. So we're going to work through an example today. The example is basically a numerical integration problem. It does an approximation of pi. In Tim's words, this is really the hello world of parallel computing. This is the very first real problem that you get assigned to when you work through the OpenMP tutorials. So I wrote this code myself from following the OpenMP tutorials. They have a channel over there, and that's what where that video came from. So this is my code based on their problem. I'm not going to really go into a background of what this actually does. That's on their channel, which you can very easily go and find. But essentially what it does is it performs numerical integration using a technique called Riemann sums, which is the very beginning of calculus. It's integrating a function, and this function happens to be the actual definition of pi if you have the exact integral. But since there are no numerical techniques to give the exact integral, we iterate and essentially calculate the area underneath the curve using Riemann sums. That's the beginning of calculus. Tim mentions this is in the way back in kindergarten. But I want to walk you through this example and what it takes to get it to compile in OpenMP, and then we'll see how it performs in QCC. So back in a minute. Okay, so we have here my a VM on my local machine here, and I'm logged into a pretty big AMD server. This is it's an AMD Ryzen Threadripper. I've got 32 logical cores because it supports hyperthreading. That's 16 physical cores, and I've got 126 gig of RAM here available for me. So that's the machine I'm gonna. It's an x86 machine. I'm gonna run my experiments on, walking you through the results for OpenMP comparing to QCC. I have here on the left the code that I just described. This is basically a very simple program. It takes an argument, which is the number of steps. Turns out this code will converge to 13 significant digits of pi in about 350 steps, or something close to that. But to basically emphasize the runtime here, I'm going to pass in a very large number, like 2 billion. In Tim's examples on OpenMP, he suggests passing in 1 million. I'm going to crank these numbers out just to demonstrate the larger the number of steps, the more accurate the integration is, and the longer the runtime is, unless you parallelize it. So this is the starting code, right? There's no pragmas. There's nothing in here that would give any tool any hints about how to parallelize it. So first thing I'm going to do is compile this code with GCC. So that's GCC, and I'm going to choose optimization level 3. I'm going to do that the same optimization level for all of these experiments. And I'm going to choose pi1.c, and that's pretty much all I'm going to do. I'm going to run it, time a.out, and I'm going to pass in 2 billion. So that's 2 and 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And see how that runs. So this is single thread GCC. It computed pi to 13 significant digits, and that's the correct value. And it took about 2.43 seconds, just using the default output of time on a single thread, a single core. I'm going to do the same thing now with QCC, and I'm going to choose the same optimization levels, so it's an apples to apples comparison, pi_1.c, and I'm going to add the -mt option for multi-threading. That basically tells the tool to automatically extract parallelism and create a team of threads, and it's going to compile roughly the same compile time as GCC, and I'm going to run it now using the same arguments. So I'm going to do time CQ run. Our runtime is embedded in a database inside that's generated from the QCC command. So I'm going to -mt, tell it to run 16 threads, and I'm going to run pi_1.cq. That's the database that the compiler created. Inside that is the host executable that will run. And then I'm going to pass the same number of arguments, which was 2 billion. And I'm going to measure the runtime running on 16 threads. So that same code, no changes, no pragmas, no rewriting. Computed pi, the same level of precision, 13 significant digits in 0.238 seconds. So that's pretty fast, and obviously we did that with no code modifications. But I want to really walk you through what the process of getting this code from the starting point of an algorithm described in C to running it in OpenMP, because OpenMP, like the pointy-haired boss says, is just comments in your code. So I'm going to quit this, and I'm going to basically open up the next level of, actually I'm going to do it with vim diff. Oh, let's do it with vim. pi under 2.c. So the first thing that you're going to do from that starting point is start adding in the pragmas, right? This is the most obvious thing to do. Okay, OpenMP, I'm going to compile with OpenMP, tell it to run everything in parallel. And I basically chose the meat of the algorithm here to basically tell it to parallelize everything here. And you should, since this algorithm is what we call something that's basically incredibly parallel. It's only dependent upon the value for x, so it really should scale quite a lot. So I'm going to compile that first, because that would be the first thing that you would try. Add in the pragmas to tell the OpenMP compiler to compile. All right. So I'm going to go back to my GCC command. In order to compile with OpenMP, I'd add the -f OpenMP. And I'm going to change it to, well, I could compile it with pi1. Let's do that just to see what happens. It's -f OpenMP pi1.c. And I'm going to run, I forgot we need to, let's see, history, grep -I, OMP. Yeah, so I have already set the number of OpenMP threads to 16. I'll do that again just to prove to you that I told it to use 16 threads. And this is, of course, the first version here. It has nothing, no pragmas in it. So we don't really expect this to work, but I'm going to just run it to prove. So time a.out for 2 billion iterations. It was a little bit slower, right? If you recall before, first time it ran 2.47. It ran a little slower with OpenMP with no pragmas. So I'm going to do this experiment again. This time I'm going to run the second version that has the pragma OMP parallel, which would be the first thing that you would probably try. And let's change that to be number 2.c. And let's time it again. All right, so I added in pragma OMP parallel, told it to parallelize all this stuff. I gave it 16 threads, and lo and behold, wow, it took 2.8 seconds. So it got slower. That's pretty typical. You keep studying OpenMP and you realize, well, okay, there's more stuff I need to do here. I need to tell it, not only do I need to tell it all the code that needs to be parallelized, but I also have to tell it what the for loops are. So let's vim-diff these, and so you can compare the changes that I make as I go along here. I'm going to compare it to pi1.c, which was my starting point. And you look, I've got to add in pragma OMP4 into this the next version of the code. That basically tells it to thread parallelize everything inside the for loop. So let's try that and see how that goes for us. So pi3.c, and I'm going to time the output again. I told it to go 16 threads, and you're like, wow, that was fast, 0.23 seconds. But we got the wrong number. We got the wrong answer. It's not pi, 0.16. Now, why is that? Well, this is because of the issues with race conditions. So then I talked about this in the presentation. What's happening is some threads, it gave it 16 threads, are writing back to this sum value before others are, so you can get the wrong number. And now you need to dive in even further and start to understand synchronization techniques. The piece of code I showed you in my diagram said I need an OMP critical to tell the tool not to write back to that value for pi. It has to do that in a serial fashion. It can only do that once. And you keep studying and studying. And if you're like me, this was over the course of many days, almost a week of studying this code. You began to understand this thing called a reduction. So pi_4.c is adding, in addition to the for, I have to tell it to create a reduction, which basically builds a dependency tree and tells it based on the value for some to basically prevent those race conditions and still enable parallelism, right? So this is the last version of this code that I'm going to show you. It's actually quite a lot of work to arrive at this simple version of the code. So I compiled version 4. Now we're back to getting the correct answer, and we're in 0.269 seconds, whereas the version with QCC ran in 2.38. So you can measure actually quite a bit more accurately down to the nanosecond using a monotonically increasing time function inside the code. So what I'm going to do just to demonstrate this is I'm going to sweep all of the values of multi-threading from 1 to 18, and then I'm going to compile it with QCC, compile with GCC with OpenMP, and sweep across all values of multi-threading of number of threads between 1 and 18, and I'm going to measure the runtime. I've already scripted that up, so I'm going to run that right now, and then we're going to actually just plot the results. So it compiled, ran GCC, ran QCC. Now it's running with each number of threads between 1 and 18, and I've already done this, so while the more threads, it's actually going to run faster. I'm going to create a plot of this using matplotlib and Python, and we're going to see what this value looks like. So across here we have green is our baseline, that's single thread GCC. All of the red bars are OpenMP with the number of threads that it ran on, and all the blue bars are QCC with multi-thread turned on. So you can quickly come across here and you see that the best number here is 14.88x speed up on 16 threads compared to 1405 with OpenMP. So as you can see, we'll switch back to my presentation. The results are pretty good here. So I've imported that graph that I just showed you, and I'm going to highlight the best results here, which is obviously the items in blue are our results, items in red are OpenMP, and the green was our baseline. But basically with QCC, the benefit are really you can save days and weeks of experimentation with automatic parallelism extraction using multi-threading. I've demonstrated that it's comparable to and even 6% faster than OpenMP when you measure down to the lowest levels of granularity down to the nanosecond. You see that we were 6% faster than OpenMP, which is 15x faster than GCC with no code modification. So in spite of what Tim might have you believe, with their automatic parallelism extraction really is possible. So I appreciate your time. Thanks for watching. You can find us on the web at CacheQ.com. You can subscribe here to our YouTube channel. You can also follow us on LinkedIn. We'll be publishing white papers and articles as we promote our technology. And if you wish to reach out to us directly, you can email us at sales@cacheq.net. So thanks a lot. Bye.